Hello. In the last lecture, we talked about the earthquake loads, and in this lecture too, we are going to be continuing discussion. Just to kind of reiterate, this is we are doing earthquake response analysis, and this is again for single degree of freedom structures. Okay. So, therefore, there is no question of that we are still looking at single degree of freedom structures, excepting that we are looking at earthquake. And last time we saw that in this particular case, there are certain aspects, just to revise very quickly. Okay. The acceleration time history is what we typically define, and this is again specific for a specific. This is a specific, but note that there are certain aspects to it, and that is that there is a toing and froing of the ground motion. Okay. So, if you look at 0, it goes to plus, it goes to minus, it goes back. So, one of the things about an earthquake ground motion is that the structure is subjected to many reversals of motion, many reversals. Just look at the reversals that you have in this particular case. Okay. Now, so that was essentially what we saw was that the acceleration time history is one way of defining a ground motion. Okay. The other way, SD, which is the U max, then SV, which is and these are functions of time and xi. SV is given such that the maximum energy, strain energy, is given by half m s v squared, okay, or you are given by the pseudo acceleration spectrum, okay, which is S A pseudo acceleration spectrum, and this essentially gives us the peak force that the structure is subjected to, and that is equal to m s or W S A by G, where S A is given by this. We also discussed the specific forms that S D becomes 0 at t equal to 0 and is equal to u g max at t tending to infinity. S A is equal to u double dot, the peak ground acceleration at time t equal to 0, and is equal to 0 at the t equal to infinity. Okay. So, we looked at them, and S V, the way S A, S V are connected to each other is that S A is equal to omega S v is equal to omega squared S d, or this is how they are related to each other. So, understand that this is the true deformation spectrum, the other two are pseudo, but however, they are important because each one represents this particular aspect of it. Okay. So much for this. Now, if I were to plot S A, S v and S d together, this is known as a tripartite plot. Okay. So, if I were to plot it on a tripartite plot, okay, how would I plot it? Well, this is the way we typically plot it. S v is plotted here, time period in seconds is plotted here. Along this axis is your S d. So, what we have is, so this is S d, and along the 45-degree other axis is the S a. Okay. So, this is what a tripartite graph looks like. Now, why are we able to draw this? Well, because of the fact that if you were to look at it, S d is equal to S v upon omega. So, it is equal to t upon 2 pi into S v. Okay. So, in other words, what happens is the S d is plotted along this line, and if you look at S a is equal to omega S v, which is equal to 2 pi S v upon t. So, this is plotted along this line. Okay. So essentially, this is, in other words, these are lines of equal S a, okay, and these are lines of equal S. Okay, and typically, tripartite graph is typically plotted in log scale. Okay, it's plotted in log scale. So now there are certain interesting things that happens. That if you were to look at this one, okay, what will happen at this is time period t equal to 0, okay, well, almost 0, because this is a log scale. So, it would probably be 0.01, and you would have 1, 10, 0.1, 1, and then 10. Okay. So, this is your time period. So, at this point, if I were to plot it, if I were to plot S a, how will it look? It will go something like this, where in this portion it remains very close to the acceleration, and then it starts climbing, goes somewhere here, and then it goes in this fashion. And so, if I were to plot the, let me call this as my u g max, peak ground acceleration. Okay. Along this is my plot of peak ground displacement, okay, and somewhere over here I am going to plot the peak ground velocity. So, along this is my plot of my peak ground acceleration, because that is along a constant S A. This is along constant S D. So, this is a plot of the u g max, the peak ground displacement, and S V represents a velocity. So, I am a constant over this actually represents the peak ground velocity. So, if I plot those, and if I plot this curve at very large time periods, what happens? At very large time periods, the deformation spectrum becomes the same as the ground spectrum. At very low time periods, the spectrum essentially is u g max, okay, and in between this plot that I have drawn over here is really the same as this particular plot which I have showed you. All these three plots are actually plotted here. Okay. If you look at it from this perspective, I have plotted, this is what I have plotted. Okay. This is of course for a particular say 2%. Okay. So, if you look at it from this perspective at S v, this is what I have plotted. If you look at it from here, right, from here, what have I plotted? See, it is going to 0. So, this is 0.01. At 0, it will go to 0, okay, and it is going up, and then the maximum value is really your. So, here actually in this region it probably goes somewhere across and then comes down. Okay. So, that is how it is. So, this will go, if it is 2, it goes to 4 and comes down. So, this is how in real fact it looks. Okay. So, if you look at fractional deformation, this is what you are looking at. This is this plot. If you look at in this direction, right? If you look at it in this direction, this is the plot that you are getting. Okay. Now, if you look at it straight, this is the plot that you get. Okay. And around 1 it goes high and then it comes down, and if you look at it from this perspective, again the difference between these is that this is a log scale plot, and therefore, this is a linear scale plot. These are linear scale plots. But if you really look at it, this is what is happening. Goes up, it peaks at about 0.3, 0.4 seconds, and then it comes down and it goes to 0 as you go higher and higher. So, you see all these three plots, I have plotted it in one particular plot here. And it actually shows me something very, very interesting, and that is that there is a zone. Okay, this zone is about till here, where it is acceleration, the response spectrum is acceleration controlled. There is a zone here where it is displacement controlled, and the central region, if you look at it, this is somehow in the zone where u g is max. Okay. So, this zone is the velocity controlled zone of the spectrum. So, you see the tripartite plot is a very, very powerful plot. It actually here what I have done is I have plotted the spectrum, all three spectrum. You can see, as I told you, you look at it this way, you see the acceleration spectrum. You look at it this way, you see the deformation spectrum. You look at it this way, you see the pseudo velocity spectrum. All three spectrums are on the same, basically because they are all related to each other. This is how it is. This is how it is. Okay. So, in this particular case, ln of SD is equal to ln of SV, okay, plus ln of t upon 2 pi. Okay. So, SD basically becomes in a way y. Okay. This is the SD. It basically becomes mx, right. You look at this, this is nothing but mx by t plus y. Okay. And so, here and ln of SA is equal to ln of SV minus ln of t upon 2 pi, which is why it is along this direction. Okay. So, the tripartite plot is a log scale graph. This is very important to remember that all the scales are in log scale, okay. And this is in meters per second, this is in meters or millimeters, and this is in meters per second squared. These are the units, okay. And the way this graph is plotted, it gives you very much where the acceleration controlled region is, where the displacement controlled region is, and the central is where the velocity. So, in other words, inertia controls all structures in this area is controlled by inertia. Okay. So, therefore, in this region what you have is that m into S A is going to be determining how the structure behaves. In this region, the displacement controlled region, m into S A is going to be very small. So, it is not inertia, it is displacement controlled. In this zone, the peak displacement, ground displacement is what is going to determine the peak response of the structure. And in this region, it is really energy controlled. Okay. So, therefore, short period structures are acceleration controlled. In other words, they are force driven, inertial force driven. In the very long period structures, okay, short period structures, inertia driven, acceleration determines the peak. I mean, that is where the acceleration determines. So, S A determines what you get. Okay. Then you have the very long period structures, where SA does not give me anything, it is displacement controlled, the peak ground displacement gives me, and therefore, it is really the deformation that determines how much the the structure, what kind of forces the structure is subjected to. And in the middle you have a situation where it is really the velocity controlled, and therefore, the energy is important, and the energy absorbed by the system is important, and neither. So, it is essentially driven by the absorbed energy from the earthquake that determines this region. So, you see, and so therefore, between extremely short and extremely long is where the energy determines what the response of the structure is. Okay. So, this is very interesting, and once you have this, we can go directly on to something very important, and that is ultimately understand all that we have talked about till now is the response spectrum for a particular ground motion. Okay. And then it becomes very important that, well, how do we define the design response spectrum, because after all you never design a structure for a particular ground motion, because once a ground motion has occurred, you cannot design a structure for it. And it is very interesting that even at El Centro, okay, there was an earthquake in 1940, okay, and that is the most famous one which I have just shown you. This is the ground motion that you get. Okay. This is the ground motion that you get at the same place. Okay. So, let us assume our building is built at this place. Okay. 1940 ground motion gave us this. The 1971 earthquake gave completely different ground motion. So, it will be a completely different response spectrum. Okay. Then in 1994 Northridge earthquake, you had a completely different ground motion again at the same site. So, obviously, you cannot design, even if you have past earthquakes at a particular site and you want to design. See, understand that all that we are doing in structural dynamics, let me review the point. All that we are doing in structural dynamics is not do dynamics for dynamics sake. It is to determine the peak response of structures to given dynamic loads. Okay. So, therefore, if you have an earthquake load, you want to be designing a structure for earthquake load. And the problem that happens here is that this is not a deterministic, it is not a load that I know. For example, I know my weight. Okay. So, I can say that, look, this is a known load. However, an earthquake, as I told you, the same station, the El Centro station, in 1940 saw a different earthquake motion. In 1971 saw another completely different motion. In 1994 Northridge earthquake, it saw completely different. So, therefore, even for a particular site, it becomes very problematic as to how to design a structure for a given earthquake. And well, there are various other ways of doing it, but one of the first ways of doing this particular problem was to define what is known as a design spectrum. Okay. So, we define a design Now, how did we design a response spectrum? And here I am looking at something that Newmark developed almost 50 years ago. Okay. So, I am going to look at something that Newmark developed and look at it from that perspective. And what did he say? Well, he said the following, that look, and now I am going to plot the acceleration spectrum. Okay. He talked about the acceleration spectrum. So, I am going to plot S A by T. He said that look, I am going to break up, and this is based on what we discussed over here, and from these tripartite plots for variety of ground motions, and plotting them, they discovered that look, there is a situation where I have an acceleration controlled. Okay. So, if it is acceleration controlled, okay. So, acceleration controlled region. So, this is acceleration, this is velocity controlled, this is displacement controlled. Again, so if we plot it this way, what he said was that look, in a portion of this, what is this? This is definitely the peak ground acceleration. Now, there is a completely different aspect, and this I am not going to go into, and that comes from seismology, which determines design peak ground acceleration. So, this is something that we know. I am not going to go into that detail. This is a structural dynamics course. In the earthquake engineering course, we could spend some time on discussing this, but here this is known. This is a known design parameter. Okay. So, Newmark said that look, this is what happens. Then we have this kind of a situation, and in the acceleration controlled region, part of it has this, and then part of it is this way. Then I come to the velocity controlled region. In the velocity controlled region, and this is a log scalar. In a velocity controlled region, it is going to be a constant velocity, and in the displacement controlled region, it is going to be this way. Now the question becomes, since I am drawing S A, okay, S A in this zone is equal to U g max. Okay. Then you have a transition zone, and then it is a constant S A, where S A is equal to some d times U g max. Okay. Then we come to the zone where velocity controlled. In velocity controlled, S A is proportional to 1 upon t. Why 1 upon t? Well, let us look at it. As V is equal to omega S d, okay, and as V is equal to 1 upon omega S A. Okay. So, in this particular portion, this is a constant. In the velocity controlled, this is a constant. So, what you have is S A is equal to constant into omega. So, that means it is proportional to omega, which means it is proportional to 1 upon t. Okay. Then in the displacement controlled region, S d is a constant, which is equal to U g max. Okay. So, if S d is a constant, then S A is proportional to omega squared, and so that is proportional to 1 upon t squared. So, in this zone, S A is proportional to 1 upon t. in this zone, it is given in this fashion that there is a transition zone. For one part it is a constant, it is u g, okay, and then for another part it is this way, and then this goes down, S A is proportional to 1 upon t squared. And the proportionality constants of course depend on this d, this proportionality constants, all of them depend on, actually they depend on xi. Okay? They depend on xi, and the transition points, okay, also depend on xi. Okay? And Newmark actually developed a specific way of determining these from past earthquakes. Okay? So, but in a sense the point still remains that you have an acceleration controlled zone, a velocity controlled zone. Acceleration controlled zone, S A is a constant for all practical purposes excepting for a transition zone, because you need to go from peak ground acceleration to some time, some number of peak ground acceleration. Okay. So, therefore, there is a transition zone, but in the velocity controlled zone S v remains a constant, and in the displacement controlled zone S d remains a constant. So, automatically S A is equal to some constant times 1 upon t, and S A equal to some constant times 1 upon t squared, and this in essence is your design spectrum. Okay. And interestingly enough, if you really look at the pseudo acceleration response spectrum, okay, now if you look at one of them, it becomes very, very difficult. But you can actually see that if you look at this, that in this zone, okay, this is almost a constant. Now, note that this is linear, and mine of what I had plotted over here was a kind of a log scale. Okay. This was a log scale kind of a thing. So, try to see in a log scale. In a log scale, this part becomes very small. Okay. So, if you look at this, this is the part where the displacement starts controlling, and you see over here the way it is going is that it is almost going down as 1 upon t in like a hyperbolic kind of a situation, and beyond about 1.2 seconds you will see that it starts going down at about 1 upon t squared, because if you look at it, the spectral velocity, this is the zone in which the spectral velocity is controls. So, that is between about 0.6 seconds till about 1.4 seconds. This is where the velocity controls, and if you look at this, this is where the displacement starts. So, about 1.6 seconds, this is where displacement starts controlling. Okay. And so, therefore, if you look at it, in this particular case, we can almost say that this goes from 0 to about 0.6 seconds. This goes to about 1.5 seconds. So, approximately this is what we see, right. Spectral displacement from about 1.5, 1.6 seconds is where displacement starts controlling. If you look at this, this is where acceleration controls from about 0.6 till about 1.5, and acceleration between about 0 to 0.6. You see how what we are looking at really comes out even in one single this thing. And although the design response spectrum is not based on one ground motion, it is based on many ground motions. And so, if when you do these kind of peaks and valleys that you see in any one particular ground motion actually gets kind of evened out, and you will see that you will get somewhere over here. So, this is 0.3, for 5G it is about 0.8. So, that is about 2.67. Okay. If you go to 2%, this is about 1, so that is about 3.2. So, you see you start getting these numbers 3.2, 2.67 for 5%, it's about 2.67, for 2%, it's about 3.5, 3.6, and you start getting numbers that the design response spectrum that Newmark talked about, you start seeing them in this particular case. So, that is the interesting part of how the design response spectrum is developed. Okay. And all of this became probable because it was put in the tripartite log, and it became very obvious that the tripartite log scale gave us the acceleration controlled region, the velocity controlled region, and the displacement controlled region. So, you see how step by step and by using the characteristics of the response spectrum, okay, you can go step by step from a time. Now, it is very difficult. You see, it is much easier to define a design response spectrum than to define a design ground acceleration time history, isn't it? How on earth am I going to be able to get any defining unless I define? See, understand that if you are looking at design, okay, when you are looking at design, you need to look at certain characteristics in whatever you are looking at to be able to define a design load. So, you always, whenever even when you are looking at loads, any load, for example, live load, you look at certain characteristics of live load, okay, and based on that, that is what you get, how you develop your design load. So, it's very, we saw how we went step by step through the entire process by looking at specific aspects from specific behavior of structures. We went to see how each response spectrum had specific characteristics. Then we put it together in a tripartite log plot, and we saw that, well, in certain zones, certain parts of the ground motion are controlled, and from that we went one step forward to getting the design response spectrum. Okay. So, there, unless something has a characteristic built in, you cannot get any design load for that. Okay. Now, let us look at the ground motion. Look at this ground motion. Does it look like anything? Can you define anything? For example, the only defining characteristic is the peak, and that also is something that we know that we can define. But can we define the time history of this? So, therefore, time history is something that it is impossible to define a design ground motion history. What is done? I will explain that. You must have heard somewhere, if you are, especially if you have been working in a particular in an organization that does earthquake response analysis, and you would have heard of, well, there are design ground motions. These are called spectrum compatible ground motions. Okay. And here the point becomes that ground motions, okay, do not have characteristics that we can pick up. What we try to do is look at a spectrum where we know that we can get a design spectrum, and you see there is a given a time, given if you are given this, going from this to SD, SV, SA is unique. Why? Because all you have to do is that SD is equal to Okay. So, SD is, if you have this time history, this is a known time history. By solving this now, whether you solve this or whether, we've already talked about various ways of solving a problem. The Duhamel integral can be solved numerically, or you can do time marching schemes to get S, whatever. Okay. Once you get your displacement deformation time history, from the deformation time history you take the peak value, and that is SD. Once you know SD, you know SVSA. So, at a particular, for a given structure with a time and this, you going from this to this is unique. In other words, it is given this, you can find these out. Okay. That is not an issue. The issue becomes that typically what is our design? Our design, for a given time history, for a given time history, acceleration time history, you can find out the response spectrum. We have already done that in the last lecture, and we have shown it in these kind of things. Okay, that given this time history of L center ground motion, right, you can get the spectral deformation, get the spectral velocity, get the pseudo acceleration spectrum. You can get these. These are unique. You can get them. The problem that happens is, if you, now as I said, a design spectrum gives you what? It gives you SA, and from SA, SV and SD. These are given design response spectra. I just talked about it. So, this is given. Now, given this, can you find out UG of t, which is the acceleration Can you find it out? Well, problem, right? There is no equation like the one that I had given, which was this is equal to So, the problem becomes, if I know this, and this is as a function of t and xi. So, SD as a function of xi and omega, okay, this is known. So, this is like a problem where I know this, and can I find this? Impossible, does not it? If there was something that said that, look, UG double prime t is equal to SD into something something something. Okay, if that was there, then I would be able to find out UG of t. But there is not a single equation that gives UG in terms of SD or SV or SA. Okay. So, you have a problem in which this is known as what is known as a classical inverse problem. If you know one thing, finding out the other thing is really, this is an input. The input is the time history. You have a kind of a box that represents the structure. Okay. And what is that? That is given by h of t, which is the impulse response function, unit impulse response function h of t. H of t is nothing but this, right? This is h of t minus tau, remember? Okay. So, so what happens is, input is, let me just draw this in a, it will be interesting for you to look at this, that what we have essentially is something like this. Mathematically, input is acceleration time history, and output is SD, SV and SA. Well, actually the original output is U of t, this deformation history, okay, and from that we derive these things. Okay. These are of course for various. So, in other words, how to get SD, SV, SA is this gives us only one value of SD, SV, SA for a given t and xi. So, we have to keep doing it. Now, this structure is defined by m, t and xi, okay, and this is the structure which is represented either by h of t, the unit impulse response function, or h I omega bar, which is the complex frequency response function, depending on whether you do time domain analysis or frequency domain analysis. Note that acceleration time history actually is like a load with finite duration. Okay. So, all the things that we talked about 2 lectures ago, all of them become valid, and given this you can find this and then all of these. Now, the reverse problem where you know these and you want to find out this is actually this. This is a forward problem, and this is known as an inverse problem. Okay. So, given SD, SV, SA, finding out acceleration time history is actually a classical inverse problem. And what is even worse is that SD, SV, even if I had the deformation time history, okay, there would be some ways that would be actually a classical inverse problem. Given the deformation history, finding out the acceleration time history is an inverse problem. Okay. What makes it even doubly difficult is that, look, we do not even have the deformation time history, because all we are picking up from the deformation time history is the peak value, and that is my one SD value. And so, when I give the spectrum, all I have it is with time period, it is all for different structures, right, all for different structures and for different damping. That is my response spectrum. How on earth am I, it does not even represent that spectrum does not even represent a particular state. It is actually many states that we are representing on one graph. So, the inverse problem is actually practically impossible. Okay. However, people have tried to solve this problem, and therefore, you must have heard, I do not want to go into the details of how they have solved the problem. You need to go into a deep mathematics to be able to solve it, and what you get then is what are known as spectrum compatible acceleration time history. Okay. Now, my final question to all of you is, does it really matter? Where do you require acceleration time history? The only place where you require design acceleration time history is where you need to do time stepping, need to apply time stepping techniques. And I did talk about where time stepping techniques are required. They are required for nonlinear structures. If you have a linear structure, and this is of course, we are looking at single degree of freedom system. If you have a linear structure, SA, SV, SD is all that you require. Okay, because why? Well, Fs max is equal to MSA, SD is my peak deformation, and peak strain energy is equal to half mSv squared. You see, if you have a single degree of freedom linear structure, the design spectra themselves give me all the responses that I am interested in, the design responses that I am interested in, the peak value of the force. What do I design the supporting structure for? Well, for M into SA. Okay. What is the peak deformation that I am likely to see, so that I can then design certain systems to take that deformation? Well, it is SD. What is the energy that is absorbed by the columns, so that there are certain things in which if they are exceeded, that fails? Well, that is half mSv square. SA, SV, SD gives me all the information that I require, and these I have already looked at design spectrum. And therefore, if you are done with response analysis for earthquake, if you are given design response spectra, you do not need anything else. You do not even need to know where those response spectra have come from. They are design response spectra, you use them, and that is what is used. If you look at the Indian code IS 1893, IS 1893 is the earthquake code. If you look at it, 1893 2002 part 1, if you look at it, you will see a design response spectrum, and you will see that you design a structure for certain percentage of the weight, and that is nothing but weight into SA by G. Okay. Thank you very much. That brings me to the end of all the kinds of loads that I am going to look at for a single degree of freedom system. In the next lecture, I shall start off with looking at structures that are not obviously single degree of freedom systems, but we can treat them as single degree of freedom systems. Thank you very much. Bye bye.